When we're looking at a rational function in this form, it's really easy to see the horizontal and vertical asymptotes. That's the strength of this form, this mixed number style format. We can see that horizontal asymptote of 2, and we can see the 1 over x minus 1 giving us our vertical asymptote at x equals 1. So not officially, but I refer to this as like a mixed number style. That's like a mixed number style of representing this rational function. Yesterday we talked about adding these things together. This is the number 2 3/5. This would look like 2 3/5. It's a mixed number. There's a whole number part. There's a polynomial part. That's like the whole number. And then there's this fraction part. The reason that mixed number style is very easy to read is that it splits up what the function has. It splits up between the stuff that cares about what's far away from 1 and the stuff that's significant close to 1. When x is close to 1, the fraction is very important. That's what causes that vertical asymptote. When x is close to 1, the fraction is that most important term. For x near 1, the fraction is the big term. When x is near 1, the fraction is the important term. Because we know as x approaches 1, 1 over x minus 1 will go to infinity or negative infinity, become very large. So the reason for that is that limit at least from the positive side of 1 over x minus 1 goes to infinity. The limit doesn't exist, but we can say that it's going towards infinity as we approach 1 from the positive side. And the limit as x approaches 1 from the negative side of 1 over x minus 1, that goes to negative infinity. The closer we are to 1, the bigger that fraction is. It overpowers the 2. But for x far from 1, as we get farther away from 1, the important term becomes the 2, because that fraction, the limit as x goes to infinity or negative infinity, that fraction is headed towards 0. For x far from 1, the fraction matters less, and the 2 is what's important. The limit as x goes to infinity, we're moving away from 1 of 2 plus 1 over x minus 1 is 2. Far from 1, the fraction is 0. Close to 1, the fraction is everything. If x goes in the other direction, if we can get a little loose with our notation, as x, the limit as x goes to plus or minus infinity, this function is going towards 2. The fraction, far from 1, the fraction doesn't matter. Near 1, the fraction is all that matters. And that's what's useful about this mixed number style. We see what's important far from 1 and what's important close to 1. We didn't see this as much in the if we add the fraction. So if we do some algebra, get a common denominator, this is 2 times x minus 1 plus 1 over x minus 1. So minus 2 plus 1 is minus 1 over x minus 1. This 2x minus 1 over x minus 1, if we add things together, if we add the fractions, we get this improper fraction style. So if we add the fractions, if we add the 2 plus 1 over x minus 1, get a common denominator, add the fractions. In the improper fraction style, we still see very clearly that vertical asymptote at x equals 1. So that's still obvious. And the limit as x goes to positive or negative infinity is still going to be 2. Because we've got a 2x over x. So we can still our thinking is a little bit differently. Our thinking is a little bit different because instead of just seeing that 2 sticking right out, we have to think about what happens when x becomes very large. When x becomes very large, I only care about the highest degree terms. When x is a billion, I care about 2x, not minus 1. If I say, here's $1 billion, it's going to cost you $1. You're not going to be like, oh, they're going to cost me a whole dollar. It's like, oh, dude, this is $2 billion. You don't care about $1. Does that make sense? When you have $2 billion, you don't get to care about $1 anymore. If you do, you're very bad at understanding numbers and you shouldn't be allowed to have $2 billion. But when x is very large, this is really just going to be the limit as, this really is just going to be 2x over x, which is 2. That's not different than what we had before. We're just thinking about it differently. We have to think in terms of this limit rather than just looking at the 2 sticking out saying, far from 1, 2 is important. Questions? From an algebra standpoint, going from this mixed number style to the improper fraction style, that's just adding fractions. Going backwards is long division like we saw yesterday. So going from mixed number style to improper fraction style going this direction, that's just addition. And going backwards from improper fraction style back to a mixed number style, we can get there with just long division. That's the same thing that we did when we had mixed numbers and improper fractions that weren't rational functions. We do the same thing. We think about it the same way. Let's think about what we see in this rational function. First of all, it's in an improper fraction style. The improper fraction part is when the degree of the numerator is greater than or equal to that of the denominator. That's what gives us this improper fraction style. Since we're trying to make this connection between rational functions and rational numbers, in improper fractions, if the top is bigger than the bottom, that's an improper fraction. But what does the top being bigger than the bottom mean in terms of rational functions? In this case, it goes by degree. Since we're looking at a ratio of polynomials, if the degree of the numerator is greater than or equal to that of the denominator, that's an improper fraction style. In this function, we can clearly see our vertical asymptote at x minus 1 because it's not going to cancel with anything in the numerator. So we see the vertical asymptote. At x equals 1. That part we see right away. That's the first thing that we're going to be looking for. That x minus 1 is not going to cancel out with anything from the numerator because the numerator is not factorable. But when we look at the limit as x goes to infinity or negative infinity, we don't get anything useful. We just see that the function goes off towards infinity, unless we look a little bit more carefully. If we look at the limit as x goes to, well, positive or negative infinity, it's not going to matter, of x squared minus x plus 1 over x minus 1. The thinking that we want to have here when we're looking at limits at infinity of rational functions is the degree of the numerator and the degree of the denominator. The only term that matters when x is very large is the highest degree term. When x is a billion, you do not care about 1 billion when 1 billion squared is on the table. You don't care about the 10 when the 100 is on the table. That's a little bit too close. Those are realistic sums of money. You don't care about $1 million if 1 million squared is on the table. When you have $1 million squared dollars, you don't care about 1 million. Does that make sense? I know it sounds crazy to like normal people to not care about $1 million, but 1 million is only a 10 to the 6th. 1 million squared is a 10 to the 12th. That's like orders of magnitude more than 1 million. If you have $1 million squared dollars, you literally do not care about $1 million. If something costs $1 million, it doesn't cost anything to you. It just doesn't cost anything. If you've got if you have $1,000 in your pocket, you don't care about dropping a penny. It just doesn't matter. So it's going to be an extra cent because it got rounded up. You're not going to be mad about that. You're not even going to notice. If we look at what happens in the long run, we know that this doesn't exist. So this goes to infinity. The limit does not exist. But if we look more carefully, if we think, since this is a rational function, if we look more carefully, we see the important thing on top is x squared. The important thing on the bottom is an x. So if we look more carefully, I look more carefully in blue. This is like an x squared over an x in the long run. So this function is going to look like x in the long run. For large values of x, we're really just looking at x. In this case, we don't have a horizontal asymptote. We've got a slant asymptote that looks like x. This is what the function looks like in the long run. So for large values of x, f of x looks like x. Now, we're looking at the improper fraction form, or the improper fraction style of this function. It's just improper fraction. There's a mixed number style. We get there through long division. And the long division works exactly the same way as long division always works. So if we do long division, everybody's terrified right now. I can tell because I just said long division and I've written down polynomials. So everybody's like, oh shit, really? Really? I'm like, oh, hell yeah, really? After Calc 2, you'll have the same feelings about trigonometric substitution. It'll be your favorite integration technique in Calc 2. I don't think I have Calc 2 in the fall, so someone else will be teaching you trigonometric substitution, which is a super bummer because it's so much fun. It's going to be your favorite, trust me. I just said, trust me. That's how you know you shouldn't trust somebody. So if I want to rewrite this in mixed number style, I'm going to take x minus 1 and I'm just going to divide this into x squared minus x plus 1. Now, if you're thinking, dude, it's divided by a monic linear, the denominator is monic and linear. Why don't you just do synthetic division? I am doing synthetic division. I'm just including more details because we need to see that this is the same thing. Now, just like yesterday when we were doing long division with numbers, we need to know how many times I can subtract x minus 1 from x squared minus x minus 1. To subtract an x from an x squared, I need to multiply by x. I can subtract x from x squared x times. I distinctly don't line up my quotients because it doesn't matter where you put the things. I'm going to subtract x from x squared x times. And then what we do is we multiply. So x squared divided by x is x. X times x is x squared. X times minus 1 is minus x. And then we subtract. So we subtract here, we get 0, and then we bring down the plus 1. I cannot subtract x from 1 without just making more fractions. So I'm done. That's my remainder. My quotient is x, and my remainder is 1. So what this tells us is that x squared minus x plus 1 over x minus 1 looks like x plus 1 over x minus 1. Now that we see this function written in its mixed number format, we can clearly see what's going on with this function. In the long run, this function looks like x, just like we had decided before. In the short run, in near 1, we have this vertical asymptote at 1. When x is far from 1, the function just looks like x, y equals x. When x is near 1, the fraction is the most important term. So we're getting a very similar function to the hyperbolas that we had before. It's just that we're taking that horizontal asymptote and pushing it up at an angle. There is a question about how deep these the bends are going to cut into these corners. But this is just a slanted variation of the function 2 plus 1 over x minus 1. But instead of having that horizontal 2, I've got this slanted y equals x. We just grab that horizontal asymptote and pull it to an angle. We can think of twisting that horizontal asymptote into a slanted asymptote. Questions? How's everybody okay? It looks so sad. Why so sad? Because rational functions too simple. If you're looking at this and thinking, dude, this is old information, not all pre-calculus classes have a lot of detail about rational functions and polynomial functions. So you're like, oh, this is old. I've seen this before. Not everybody has. So that's why I want to talk about it. What we want to recognize is the usefulness of thinking about these kinds of behaviors, thinking about the behavior of rational functions. So if I've got this function x squared minus 1 plus 1 over x minus 2, we can see what the short-term behavior is near 2. We see that vertical asymptote at 2. And we see that in the long run, when we get away from 2, our function is going to start looking more and more like x squared minus 1. So now we're past horizontal asymptote, we're past slant asymptote, we're into the, well, this is like a parabola asymptote. Will we even say asymptote if it's a parabola? That's certainly the long run behavior. So close to, this fraction is important. So we see this vertical asymptote at x equals 2. Can we call something an asymptote even if it's not a line? What we call it is not important. What we recognize is that far from 2, this function wants to be x squared minus 1. Close to 2, the fraction is more important. Some kind of metaphor in there. Like going to school far from home. Near home, you have to listen to what your parents say. But when you're far from home, you can be your own parabola. I don't know if anybody has ambitions to become a parabola, but so if we imagine what this graph the graph will look like, I'm going to give myself a parabola, 0, -1. So instead of having that horizontal asymptote and just twisting it into a slanted asymptote, I'm taking that horizontal asymptote and bending it into a parabola. And then I'm going to mark my vertical asymptote at 2. Then I'm going to realize I shouldn't put the vertical asymptote at 2 because I've got this little tiny sliver that I have to try to fit some of the graph into. But we would do the same thing. Some of the graph would be going far from 2, we're going to be close to the parabola. Near 2, we're going to be close to the vertical asymptote. So it's going to follow this down. And then as we get closer, the fraction becomes more influential. And then we'll have some sliver up in here. I forgot I didn't need to draw the parabola so carefully because it's a lot wider than this. I'm just going for the idea. That's why I shouldn't have drawn it so carefully. So all we've done is taken a horizontal asymptote, and instead of just twisting it into a slanted line, I just bent the whole thing into a parabola. Now, if we look at this graph, we can see that there's some question in this graph. So the way I've drawn it here, I've just kind of like scooted it down and kind of like have it bend towards the parabola. How do we know that it doesn't bend back up? What if it follows that closely before? We might want to know what's going on there. We might be interested in what's going on there. We can find that out because we have calculus technology now. We can figure out what's going on down here with calculus. If we look at f prime, the derivative is going to be 2x plus 0 plus x minus 2 to the negative 2. So our critical points are where the first derivative is 0 or undefined. We see this critical point at 2. We knew that that was going to be there because there's this gigantic vertical asymptote where things can change. And based on our starting point of 1 over x minus 2 to the first power, we know that the graph is going to go down one side of the asymptote and up the other side of the asymptote. But we want to see if this function has any other critical points where the first derivative is equal to 0. And so we could set this equal to 0 and try to solve. Now, a rational function, when it's in its improper fraction form, is better for solving. Actually, no, we can put the fraction on the other side. So I'm going to take my first derivative, set it equal to 0, and solve to find the critical points. One thing I can do is I can put the fraction on the other side. And then multiply. This leads to a cubic equation. And we see what happens when I don't plan my examples more carefully. Because now we have to solve a cubic equation, which is kind of a pain in the butt. We can also multiply by, you also might think of multiplying by x minus 2 squared. So maybe you think of, I see a variable in the denominator. That all works the same. Now we're getting these polynomial equations, but the polynomial equations aren't the same as our original because they're not the same at x equals 2, but we don't care because we already know what's going on at x equals 2. We're just trying to look at this cubic polynomial and see if there's a term or if there is not a term. So now what we need to think about is what could happen. How many solutions could we end up with? How many complex solutions do we definitely have? It's a third degree polynomial. For complex solutions, we definitely have 3. How many real solutions must we have for a cubic polynomial, a cubic equation? How many real solutions do we have to have? There's a clue in the graph that we have up here, even though we're unsure if the graph like bends down this way or it actually has another hook in it. 1, a cubic polynomial has to have 1 real 0. Can't get away from that because as x goes to negative infinity, it's a positive real leading coefficient. So one side goes to negative infinity, the other side goes to positive infinity. A polynomial function is continuous everywhere. So the intermediate value theorem says if we go from negative to positive, we have to cross 0 at least 1 time. So we definitely have 1 real 0. So our question is, do we have 1 real 0 because it's just this up here and this falls down? Or do we have 3 real zeros because we have a bend here, and then the bend up here? Do we have those 3 real zeros? That's the question. Because our other possibility is that we have 1 real 0, which is probably this one up here, and 2 complex zeros, which is this flat part down here. Remember when we thought I was done talking about polynomials? Surprise, motherfuckers. Polynomials are back. So the possibilities here . This is an equation. I could call these solutions. There's 1 real solution for sure because we have a cubic polynomial. The question is about the other 2. The possibilities now are either two complex conjugate zeros or 2 more real zeros. The 2 complex conjugate zeros would lead this graph to this graph here where it bends, and instead of making it turn up following the parabola, it just keeps falling down, because it does not make any turns. If we get 2 real zeros, 2 additional real zeros, then the function will bend here and we'll have a 0 down here and another 0 here, representing the 2 turns. So the 2 complex conjugate zeros would mean there's only 1 turn from the real 0. The 2 real zeros would mean there are 3 turns in the graph. Any questions? How's everybody okay? Producing a graph is not the point. If we want to produce the graph, we'll just have our calculator produce a graph. It's like, oh, did someone say graphs? Decimals, right? That's what we would do. I want to produce a graph, so I'm going to leave my graphing calculator in my backpack. So my graphing calculator is really terrible at graphing. It's good to have, it's really good at other things, but it's terrible at graphing. Now that phones have come along. Phone be like, oh, suck it, graphing calculator. Yes. But my calculator is over there, so I go, oh, why don't you find the reducer echelon form of a matrix? My calculator in my phone is like, oh, well, fuck you then. The point is that we try to connect as many things as possible. We want to make sure that we connect the things that we know to the things that we're learning about and how we can use those things and combine those things. These polynomials and the real solutions, it's not about solving this equation. It's about knowing what could happen. Knowing what could happen. Smelling the smoke, waking up, running into the bathroom, seeing the ice bucket and the faucet, and knowing that a solution to the problem exists. Comment? Slide remark? We'll have a test on Thursday that will not be this noodly. So one whole page is just, can you find the derivative product quotient change? Then another page is about increasing, decreasing concavity. That's going to do it for today. That's going to do it for this week. I will see you all on Monday, but have a good weekend. And thanks for playing.